Yeah, so welcome back, everyone. Today, Federica is speaking, and she will tell us something about this cool new research from Facebook, and it's about memory-augmented multiscale vision transformers for video recognition, and in particular, long-term video recognition. So, without further ado, Federica, please.
Yes. So this is a very interesting paper, and the authors are the ones you can see there. And they are from Facebook AI Research and from Berkeley. And they have presented this paper inside the CVPR 2022 conference. So this was a very interesting paper, as I said before. And the problem here is video recognition. So you should know that video recognition is the machine's capacity to obtain, process, and analyze videos, and in particular to understand what is inside the video. There are many existing approaches that obtain quite good results in terms of accuracy, but they are still quite limited. And in particular, the problem with existing approaches is that they parse visual content in short time periods. So we have a sort of bottleneck for clips that are longer than 5 seconds. And so what we can't do at the moment is reason across a longer range of time. And the other problem is that obviously these approaches are not scalable. So if we want to increase this temporal support, so if we want to consider a longer range of time and if we want to consider a context, we need to increase the number of frames that we are processing, but this is computationally very expensive. So this is the problem. And the authors of the paper have tried to solve this problem by proposing an approach that is based on an intuition, that is how humans are processing signals, and in particular, visual signals. So, what we are doing as humans is using this online fashion. So, we are seeing something and then we are associating what we see with past memories to make sense out of it. And then we are memorizing only important information for future use. So, based on these, the authors of the paper proposed this architecture that is called MeMViT, but I'll stop for a second because I'm going maybe too fast. I don't know if you, Giacomo, have any questions. And now this was
No,
just a quick introduction, and I'll
yeah,
go
no, I
into.
think it's pretty clear. So maybe can you explain again what you mean actually with online fashion? I sort
Okay,
of missed
so
it.
online function means that we are processing frames one at a time and then using the past frames in our memory to
Yeah, right,
information with the current ones. Instead, offline, we take a batch of frames, so a clip, and we process all of it together
right.
without
I see.
using past or future. And so
Okay,
I don't know
okay,
if it's
okay.
clear.
Yeah, yeah, makes sense. Thanks.
Okay, so this is the architecture that they proposed, and it's called MEMVIT. And MEM stands for memory, and VIT is, I don't know if you know it, the vision transformer. So I don't have the time to go too much into the details about the vision transformer because it was proposed in another paper. I invite you to read these papers, or also we could explain it in another episode. But the thing is that they are embedding this memory in the VIT architecture, so the vision transformer architecture. So the thing is, we are how does it works? Okay, so we take this video and we split it into a sequence of clips that could have an arbitrary size, an arbitrary length, and then these clips are processed sequentially. What we do is we cache inside our memory some representations of the processed clips, so the past clips at each iteration. So when we are processing the clip at time step t, the model has access to previously cached information about earlier iterations. So all iterations t minus 1, t minus 2, t minus 3, up to t minus m, that is a parameter that we can choose. And how can we do this? So instead of using the regular attention mechanism that we should know is the mechanism used in transformers that use keys and values only from current iteration, they are extending this mechanism with keys and values from previous iterations also. So at each iteration, what we are considering is a set of keys and values that comes from the current iteration and also from previous ones.
Yeah, so you're sort of gluing back. Well, gluing is not a technical term, but uh, I mean, so yeah, so you're using like the output um, of your transformer at time, let's say t, and you're also using some knowledge from the past, meaning t
Yes,
minus one, t minus two, and so on and so forth.
yes.
Okay, and how do you uh, so these things from the past, are they some sort of feature representation, some latent
Yes, they
space,
are.
some
They are the keys and the values that are extracted from the
oh
first
right,
part of
yeah,
the transformer. So it
sure,
is a
okay,
sort of embedding of representation of the previous clips.
right,
And
yeah, okay.
in the naive approach, we use all keys and all values from previous iterations, but they also proposed a method for compressing in a smart way this memory in order to reduce the memory footprint, obviously, and in order to make this architecture even more efficient. Because what we could do is we could make the model learn what is the most important information to store inside the memory. So instead of
Hmm.
storing all keys and values from past iterations, the model learns what are the best keys and values to store inside its memory. And in a sense, is what we're doing as humans. So we only memorize the important concepts, the important parts of visual signals, and then we can also forget about the less important ones.
Yeah, maybe
And
a comment on this would be yeah, I'm not sure this makes sense, but let me just try and explain it. So let's say that, as you were saying, I'm not memorizing the entire information from past times, let's say, because so I don't know. Suppose we are at time t equal 5. Let's say. So of course, like the thing at time t equals 1 knows something about t equals 0, for instance, and
Mhm.
in the naive approach you were mentioning, t equal 2 will know something about t1 and t0, let's say, and so on. But in some sense, T1 already contains some information, I guess,
Yes,
on
exactly.
T0. So
We have
this
we,
sort of
if we don't do
re-
this memory compression, we have redundant information. So
yeah,
the
makes sense.
compression
Yeah.
is in order to reduce the redundancy and to
Uh,
be more efficient. Of course,
right.
yes.
Okay. Yeah. Yeah. Okay. Makes sense.
And
Okay.
in a sense, if a video represents, I don't know, a person reading, and in the background we have, I don't know, other persons walking, other people walking, we don't need the information about the background. So the model can
Yeah.
learn that the
Yeah.
information about the background is not important, but only the embeddings of the person on the foreground is important. That is something
Yeah. Yeah.
high
Sure.
level that we could understand from this. And here you have the results they obtained. So they performed some experiments with these two datasets that are benchmarks for video understanding. And we have the AVA dataset and the EPIC kitchens. And as we can see, the model MeMViT outperforms previous state-of-the-art models in all of the cases, I guess. And um, I think that this is not the most interesting part, but this is so the benefit of scalability, because MeMViT can process 30 times longer input durations that existing models with only 4.5% more compute. So if a traditional method would have to do that, it would use 3,000% more compute to do the same, because we would need 30 times more frame in order to process more of the duration of the video. Instead, by using this memory and this technique, we could only use 4.5 more compute. And this is, I think, astonishing for me.
Yeah. Yeah.
Uh,
I absolutely. Yeah.
And also we gain this efficiency, but we also gain accuracy, so we have the best of both worlds in this case. And I think this is a very interesting paper for this, because we can obtain both gains in accuracy and in efficiency. Maybe it's one of the first times that we see this, because of course there's always this trade-off between accuracy and efficiency, but here obviously the main thing is scalability, but we are also gaining in efficiency, and that's really really good. And I don't know if you have any other questions. We can
Yeah,
also
maybe
go
just a
back
quick one, which is
tomorrow.
the usual ending question. That would be, what do I need to train this thing? So is it some super, like a
Yeah,
bunch of a 100 or something, or is it something?
actually I don't know, because it's not his written as usual. They posted the code on GitHub, so
Okay.
maybe we could use it without uh, super fast GPUs, but I'm seeing through the
And they,
paper if there's the
do they also
specification.
provide some pre-trained models? So then does it
Yes,
make
they,
sense
they only
to?
provide these pre-trained models on Ava, so you could use it as it is or test it, but they do not provide the code for training on your own data set. That is something
All right.
you should implement.
Okay. So you just have the
Uh,
inference mode, let's say.
yeah.
Yeah. Okay.
They don't no, they don't say what they're using, but I can find it. But I guess
No,
it's
no, it
not
was just a
something
curiosity. It's not.
super super powerful because of this scalability that we're talking about. So
Yeah.
here you can see these G flops. That is the unit that we can use for computational
Yeah.
cost, and it is really low. So this it is the same that we are using for baseline models of video recognition.
Right. Okay. Okay. Makes sense.
Okay, and
Okay. I don't have any further question. I don't know if you have anything to add at this point. Are you
no, I
okay?
guess that's all.
No. Okay. This was very interesting. Actually, I will give the paper a read for sure. And well, thank you for presenting it, and see you in the next episode then.
Okay, bye bye.